Hello and welcome to our lecture on ANOVA, or also known as Analysis of Variance, and the chi-square test of independence. The TOI is test of independence, the chi-square test of independence. We present this as the last lecture in the series on inferential statistics, but it's only fair to say that while some set of techniques are presented as a part of inferential statistics, most of the techniques in statistics use statistical inference in some way or the other. So for instance, after this lecture we will be talking about regression and so on, and there is a significant component there which is associated with statistical inference. But in any case, this lecture we're going to talk about the analysis of variance and the test of independence. Okay, so far statistical inference was confined to input variables that could take up two possible values, and that was the two sample cases, right? The two sample tests where you would compare two different samples, and the variable of interest would be, for instance, either male or female. So we came up with an example where we said the heights of 10th standard boys in public schools versus the heights of 10th standard girls in public schools. So if you were interested in seeing if the average height of a boy in 10th standard in public schools in India is equal to the average height of a girl in 10th standard in public schools in India, here the output, essentially you can think of, there are two variables that are involved, and you can think of the output variable as one of height, and your input variable you can think of as gender. So you have two different sets of data and you're comparing them. Now there are also these cases where it doesn't make sense to think of these as input and output variables. That's just confusing, right? So these are the single sample test cases where you just have one variable, height, and you've defined all the other parameters around it. And so it could be something like, I've already defined that I am interested in studying the average height of boys in 10th standard in public schools in India, and I'm interested in seeing if that average height is less than 120 centimeters or something, some such number. There's no concept of it. There's just one variable which is height, and that's it, and you're comparing it to some number that you had in your head. So that's essentially summarizing the two sample case and the single sample case. For the first time with something like the ANOVA, we take on a case where this variable, which is essentially like this input variable, can take on two or more states. So essentially you'll see it take on three or more states, and that's the real differentiator about ANOVA. So just to kind of give you a little bit more color on this, a standard application of ANOVA would be something like the following, where you're still dealing with an output variable that's typically quantitative and continuous, like for instance like height, right? But your input variable need not have just two states, it can have three or more states, and you're still probably interested in comparing their averages. So extending the example that we saw in the two sample t-test case, if you wanted to ask a question such as, is the mean height of 10th standard boys is the average height of 10th standard boys in Tamil Nadu equal to the average height of 10th standard boys in public schools in Maharashtra? Is it equal to the average height in Karnataka? So you were not just interested in comparing two sets of samples, but you had multiple sets of samples, and typically what you're comparing, the output essentially variable is still like a continuous quantitative variable like height. It can be anything else, but essentially it's a quantitative variable, and you have multiple discrete settings of your input variables. So you're not just interested in comparing boys versus girls or method A versus method B, but you're now going from, in the t-test you were comparing method A versus method B, you can now say, is method A equal to method B equal to method C equal to method D, or are they different or some subset of them different from the others? Okay, so that's essentially an application of ANOVA. Now the chi-square test of independence is one that can be used when you want to compare, again, multiple proportions, right? When you're interested in two variables and both of these variables are categorical variables. So it could be the same thing like Tamil Nadu, Karnataka, so the different states of India could be one of the variables, and the other variable could be the number of people at different age groups. So number of people between 0 to 20 years, between 20 to 40 years, and 40 to 60 years. So there's one variable which is the state, which is a categorical variable, and here's another variable, age, which I have in some sense made categorical. But essentially I'm just interested in these two variables which are categorical, and I'm just interested in looking to see if there's any relationship between them. Another way to think of the chi-square test of independence is see it as some form of an extension of your proportion z test, right? In a proportion z test, you would typically handle problems of the following nature. You would say, if you took a question like, are men more likely to purchase a certain product than women? That would be a proportion z test, right? Because you have two categories, men and women. It would be, to be precise, it would be a two sample proportion z test, right? Because you would have two categories, men it would be one category, women would be the other category, and their likelihood of purchasing a certain product would be represented by a binary, right? So a stream of ones and zeros. So 30% women purchase this product out of 100 samples, and 20% men purchase this product out of 25 samples, right? But you take that same problem where you had just two categories, which is purchased or not purchased, men and women, and you extend that to multiple categories on both dimensions. So that's what we did when we said state could be multiple different states, and we said age could be multiple different ages. So if you're able to take these two variables and extend them to multiple categories, you can use a test of independence in a sense. Okay, so let's first jump into the ANOVA and try and explain the core concept and the math behind it. The idea behind the ANOVA again would be to test a hypothesis of this nature, right, which is mu A equal mu B equals mu C equals mu D. A typical t-test, for instance, would have just looked at something like, is mu A equal to mu B, right? So I think a very natural question that quite often comes up is, what's so special about 2 versus 3? Why is it that for 2 you can use a t-test, 3 and more? It's that the ANOVA is built for this kind of multiple comparisons, but it works just as well even if you just want to compare two samples. So you can essentially replace your t-test with a two sample t-test with an ANOVA, and you would be doing something mathematically identical. Okay, so before we go any further, we've identified the hypothesis. Now let's get some nomenclature ready. So these are the different samples. So this is a sample corresponding to A. Okay, and A could be anything. It could be fertilizer A versus fertilizer B versus fertilizer C. A could represent the state Karnataka, B could represent Tamil Nadu, C could represent Maharashtra, whatever. So it depends on the question. Let's take a fairly consistent example. So let's take the example of height of boys in public schools in 10th standard for 4 different states. So these are the 4 different states, and this is the data set. So this is data point 1. So this is data point 1 for state 1. So that's represented as y1, 1. Now data point 2 for state 1 is represented as y1, 2, and it goes on till y1, n. And similarly it goes in this direction, y2, 1, and ultimately you have y4, n in the bottom corner. Okay, now having defined this, I'm going to throw you in some sense in the deep end with the formulas of how an ANOVA is actually computed. Okay, so this is the idea, and so let's just go through this step by step. The idea here is to compute an F statistic, right? And what have we learned about, if there's one thing we've learned about hypothesis testing, it's that you come up with a hypothesis, which we did, and our hypothesis was that mu A equals mu B equals mu C. And the alternate hypothesis, by the way, out there is that not all mu's are equal, right? Because there are many ways in which mu A that you can violate the statement that mu A equals mu B equals mu C equals mu D. You can violate it by saying mu A equals mu B but is not equal to mu C equals mu D, or you can put that not equal to anywhere in that equation. So quite simply, the alternate hypothesis is that not all the mu's are equal, right? Okay, so we took care of the first step, which is to create a null and alternate hypothesis. The second step is to do some kind of computation to come up with a test statistic. We're going to talk a little bit about how first we're going to talk about the overall structure, which is the math behind this table leads to an F statistic with a minus 1 degrees of freedom and n minus 1. If you remember, we discussed about how the F statistic has a numerator degrees of freedom and a denominator degrees of freedom, and you will calculate that F statistic, and the rest of the hypothesis testing is the same. You will then calculate a p-value and then choose to reject or not reject. Okay, now let's take one step back. We say the F statistic that we've computed here is nothing but something called MSB divided by MSC. We're going to talk a little bit further about these terms, but for now you can take this again, go one step back to these two values, and you technically don't need to know the mean square total or any of these terms. So this entire part you don't need for actual calculation of the test statistic, but it's there to give you a bigger picture. Okay, so again we say this MSB is nothing but SSB, okay, divided by something called the degrees of freedom, and that's fairly obvious in terms of what math needs to happen there. And again, the same concept with MSE. Okay, so at least we know how things flow from one side to the next. Now let's get to the core of the formula, which is calculating the sum of squares between and the sum of squares error. Okay, the sum of squares between is essentially y bar I dot minus y bar bar dot dot. What do we mean by that? Okay, so we'll talk about the terms here, and then I'll come to n and a and so on. Okay, essentially what y I bar dot means is y a bar dot is nothing but the average of all these terms. Y bar bar dot dot is nothing but the average of all the numbers here. Okay, so if I want a row wise addition, I say y a bar dot, and similarly y I would say b bar dot for this row, right? So this would be y a bar dot, this could be y b bar dot, and so on. And the idea is that if you're going to change a, b, and so on, and a, b, and c and d can be coded as 1, 2, 3, 4, then I might as well just say y I bar, right, dot, and put that through a loop essentially. So that's what I'm doing here. I'm saying y I bar dot to say I'm going from I equals 1 to a, where a is the total number of treatments, which in my particular case is 4. So there are 4 different treatments, or there are 4 different sets of samples that I'm comparing. So essentially I am taking I from 1 to 4, and I'm taking each of those means that I calculate. So I'm essentially taking this average, this average, this average, this average separately. I'm taking each of those and I'm subtracting that from the grand mean, the overall mean. The overall mean is nothing but every single output variable. This entire table, in a sense, this entire table average is y bar bar dot dot. Okay, so essentially what I'm doing out here is I'm doing something, if you look at this formula, very similar to standard deviation, but it's essentially the standard deviation of the means, right? So there's an overall mean and you have individual treatment means. So I'm essentially looking at out here, this term looks, it's not the standard deviation because I've not done the square root, and I'm not divided by the number n minus 1. In this case it would be a minus 1, so I've not divided that, so that's why it's still, I'm going to divide it. Once I divide it, it's kind of like variance, but I've not divided it yet. So out here it's essentially like a sum of squares. Once it gets divided by that a minus 1, then it becomes that MSB, right? But in concept, this is, and we're going to talk about the multiplication by n in a second, but in concept, this is a lot like the standard, the variance of the means, right? So it's like the variance. So if you were to compute a set of means for each row, right, a set of like y bars I dot for each row, the standard deviation of these values, or rather the variance of these values, is essentially what you're computing with MSB. Okay, now what's the concept behind here? Here what you're doing is you're looking at the standard deviation of each data point, right? So I comma j just means that I goes from 1 to a, which means I'm going through each row, and I'm going through each column out here. J goes from 1 to n, so j is going from 1 to n, okay? I is going from 1 to a, right? So it's literally like I'm going through each data point, right? And you know, all through this matrix, and I'm looking at the deviation of each data point from its row average, right? We saw these two are the same terms that we're using here. The concept here is that we are looking at essentially the standard deviation within each row, right? I'm not looking at the deviation of y11 from the grand mean y bar bar, but I'm looking at the deviation of y11 from this row's, essentially this row's average, okay? And I'm averaging that across every row. So it's almost like I'm taking a row-wise average of every data point and averaging that. So okay, so that's called the sum of squares error. And again, you're dividing by the total number of points that you see. It's a set of n, and capital N, by the way, out here, there's a difference between the small n and the capital N. Capital N is essentially nothing but the total number of data points. So small a is the total number of treatments. In this case, it's equal to 4. N we've not actually defined out here, but essentially it's the total number of columns, right? So that is the number of data points that each combination has, and capital N is the total number of data points. So essentially it's nothing but a times n. So a times n is capital N. So using that nomenclature, again, calculating MSE also should be obvious. Okay, so the mechanics of how you do the ANOVA with the f-test and calculate a p-value should at this point be fairly clear to you. But let's spend a few minutes and try and get a little bit more intuition on this, which is, why are we using an f-test, which we know from earlier experience is used to see the difference between two variances, right? We use the two sample f-test for detecting the difference between two variances. Now why are we using that? To calculate the difference between means, right? And the core idea is the following, that the mean square between is one way of calculating the total variance. Now mean square error is another way of calculating total variance. Now these three, which is mean square between, mean square error, and mean square total, which is what is described here, are all going to be equal in a sense. Again, they're going to be statistically equal, not actually equal, if the null hypothesis is true. So if we go back to the null hypothesis, which is that mu A equals mu B equals mu C equals mu D, then MSB, MSE, and MST will be statistically equivalent. However, if it's not true, then you will find that MSB will be greater than MST will be greater than MSE. So you've got two different ways of computing variance, and what you're doing is you are doing an F-test of these two different variance calculations, right? So you're doing an F-test on these two different variance calculations, and you will not reject the null hypothesis if the null hypothesis is true, which is mu A equals mu B equals mu C equals mu D. Now if those means are not equal, then these two computations of variance, right, don't really represent the total variance, and this computation of variance becomes an overestimate, and this computation of variance becomes an underestimate of the overall variance, and therefore a test of whether these two are different variances will show up to be true. Essentially, you'll wind up rejecting the null hypothesis that these two variances are equal, and thereby commenting on the fact that the null hypothesis of means was probably not true. Okay? So let's get a little bit more intuition on why this becomes, if mu A, if the null hypothesis is not true, and here the null hypothesis is that mu A equals mu B equals mu C dot dot dot. If this null hypothesis is not true, let's take a look at why this computation becomes an overestimate and this becomes an underestimate. Okay, so here is the first case where the null hypothesis is true. Okay, so if the null hypothesis is true, that means mu A equals mu B equals mu C equals mu D, which means the mean of mu A. So this is the distribution of A, this is the distribution of B, and this is just a sample case. So it is A, B, C, and here are the distributions. And hey, look, the means are this, the same. And here I've gone further and even made the distributions look identical, right? So if you were to take samples from A, samples from B, samples from C, and you're just going to put them all in one bucket called total distribution of Y, this is how it would look, right? Because essentially, since these distributions are identical and their means are identical, it looks this is also identical. So how do you compute mean squared error? The way you compute mean squared error is essentially look at the variance of each distribution, right? You basically take each data point and look at the standard deviation of variance of the data point with respect to its mean, right? So you're essentially computing the variance of each of these distributions and you're just averaging them. And because the variance of these distributions are going to be the same, right, that's going to match the variance of the total distribution of Y, right? And we just explained why. Okay, now let's step to mean square between. Mean square between is, so here's the total distribution of Y, and you're interested in capturing the variance of the total distribution of Y. And the way you're going to do that is you're going to take the mean of distribution A. You're going to take a sample mean of distribution A. And as you've known from the earlier part of this course, if you take 5 data points or 6 data points on A and you compute a sample mean, that sample mean need not exactly fall on the population mean, right? So you might get another value here for distribution B. Now, as long as the null hypothesis is true, which is that distribution A equals distribution B equals distribution C, blah blah blah, then you are going to get some sampling distribution if you take the means of each of these distributions. Right? If you take the means of each of these distributions, then if all of these are equal, then you're going to get a new distribution called the distribution of the means of ABC. And what is it that we've discussed about the variance of this distribution? We've discussed that as long as you're sampling from essentially the same distribution, right? You're sampling from the same distribution because A now looks identical to B, looks identical to C. They all have the same means. As long as you're doing that, we know that this standard deviation, right, is equal to the overall standard deviation, that is the standard deviation of the total distribution, or you can think of it as a standard deviation of any of these distributions because they're all identical, right, divided by square root of n, right? Or you can think of it in variance terms and say it's sigma square divided by n. Okay, so as long as I can compute this variance and then move this and multiply it by n, right, I could cancel this out and I can get an estimate of this variance. So that's what I'm trying to do. What I'm trying to do out here is I'm calculating means from each of these distributions, and I'm taking the standard deviation of those means. I'm taking the variance of those means. I'm taking the variance of those means and multiplying it by n with the belief that if the null hypothesis is true, that should be a great estimate of the variance of the total distribution. Which is fine, that's going to work great as long as the null hypothesis is true. So as long as the null hypothesis is true, this approach to calculating the variance of this distribution, right, variance of this distribution, and this approach to calculating the variance of this distribution, so the MSE approach to calculating variance of the total distribution and MSB approach to calculating the variance of the total distribution, both should work perfectly fine, right? But what happens when the null hypothesis is not true? Take this case where the null hypothesis is not true. Now, if you take the total distribution of y, right, because the null hypothesis is not true, and you get some data points from distribution A, some data points from distribution B, some data points from distribution C, it's going to fall over a much larger region, right? Now if you try to estimate the total variance, let's take a look at how MSE would estimate the total variance. MSE would take the deviation of each data point with respect to its mean, not with respect to some grand mean, right? And even that mean is essentially a sample mean that you're going to calculate, but the idea is that your estimate is going to of variance out here is going to be some value, your estimate of variance here is going to be another value, and similarly out here is going to be some value, and all you're doing with MSE is you're taking the average of these three numbers of 1, 2, and 3. Now what's the average of these three arrows? It's an arrow with a magnitude that's much smaller than the real variance, right? So when the null hypothesis is not true, the MSE method of calculating variance becomes an underestimate of the total variance. Now let's look at what happens on the MSB side, right? Now the null hypothesis is not true, and so despite the fact that there's one source of variation, which is that the sample means are not falling exactly on top of true means, right? But in addition to that, the sample means are further separated from each other because they are trying to go after a totally different line. The true means themselves are different, right? So the standard deviation, the distribution essentially of the sample means is going to be a much wider distribution because the means are not equal, right? And now when you multiply that by n, you wind up making a huge overestimate of the total distribution of y, because you're essentially out here, you're trying to look at you're trying to get sample means of distributions which have truly different means, and you're looking at the standard deviation of the sample means of distributions with truly different means. So it's going to be an overestimate of the total variance of the distribution of y. Okay, so I hope that gives you some intuition on why the F-test for the ANOVA works the way it does. But the important thing for you to remember is that the F is a ratio of two variances. Okay, and the core idea is you are using the F-test, which is used for ascertaining whether two variances are equal. You're using that in an indirect way to make a statement about the means of many distributions, and you're doing that by saying that if the null hypothesis is true, method A of calculating variance should be equal to method B of calculating variance. But if the null hypothesis, which is mu A equals mu B equals mu C, is not true, then these are not accurate methods of calculating variance. Great. The big question is, what do you do? Okay, so now we know the mechanics of it. We have some intuition for the ANOVA. But the idea is, okay, so you did this, you calculated an F statistic, you then went and plugged that F statistic and found out the probability, and let's say your p-value was really small. So you want to reject the null hypothesis. Okay, so what do you do after rejecting the null hypothesis? So what is the statement you're making when you reject the null hypothesis? You're saying, I'm rejecting the null hypothesis that mu A equals mu B equals mu C equals mu D. Okay, great. But can you tell me which of these mu's are different from which others? So one great way to do this is called the Tukey test. It's not the only way to do it, but it's a fairly common way of doing it. So that's why I've called it method 1. It's the Tukey test, but there are other methods as well. The idea here is to decide on an alpha value, which we do with many hypothesis tests. Even before we start, we say if that p-value is less than a certain value, I'm going to reject it. So let's say you start with an alpha value, and then you calculate something called the critical Tukey distance based on this alpha value. So there's a distribution called the Tukey distribution, and that's again something that you can get usually from software, or you can get that from the back of textbooks. But you'll essentially plug in the values of alpha, which you just decided one step above, and you know the value of I, and I out here is the number of treatments. So it's the equivalent of what we had as A, but I didn't want to confuse you between alpha and A, so I've called it I out here. N is the number of replicates, so the small n remains the same concept, and the large n remains the same. The only thing that I've changed is I've called what we used to call A, I've called that I, and the reason I've done that is so that I avoid confusion with alpha, right, out here. Okay, so we do that, and we use that mean squared error formula out here, and we calculate something called a critical distance, and then you do a very simple thing, which is you do a complete enumeration of all pairs. So for instance, this is the mathematical way of showing it, but essentially all I'm saying is, let's calculate y bar A dot, right, and similarly calculate y bar B dot, y bar C dot, and look at the difference between each pair of y bar I dots, where the two i's are not. So the different combinations you can come up with are, in our particular example, you'll have A comma B, A comma C, A comma D, B comma C, B comma D, C comma D. So there are 6 possible combinations, and you're essentially just taking the absolute value. So B minus A is the same as A minus B. So you just calculate the 6 differences, and you see which of these 6. It's 6 in this particular case because we had 4 treatments, right? We had 4 different, we had A, B, C and D, so you had 4 possibilities, 4 sets of data, so that's 6 treatments, because you get, the concept here is combination, so you'll have 4C2 combinations. But how many ever treatments you have, you'll similarly have the concept of whether you like to use the word I, or whether you want to use A, right, C, 2 combinations. You'll calculate that many combinations of distances, and you'll see which of these distances are greater than the Tukey distance, and then those are the ones that are not equal to each other. Okay, so you'll calculate a critical distance, and to figure out between, see, you've just rejected the null hypothesis that mu A equals mu B equals mu C equals mu D is wrong. So you've said that that's wrong, but which of these are different from each other? For that, you calculate a critical distance and see which of these combinations have a mean difference that's greater than the critical distance, and those are the different ones. Okay, so I hope that gives you an idea of what the Tukey test does. Okay, so now we move on to the next topic, which is the chi-square test of independence. Right. It's noteworthy at this point to say that we've already looked at one chi-square test. We've looked at the chi-square test for standard deviation in the case of a single sample test, and you might also encounter another test called the chi-square goodness of fit test, and that's used when you have a set of data and you want to see how well it fits to a particular distribution. Okay, but out here what we're interested in is essentially using the chi-square test of independence, and it's used here where you have two categorical variables. So here is the first categorical variable, which is the smoking habit. Is it heavy, regular, occasional, or never? And here is the second categorical variable, exercise, frequent, some, or none. And what you're trying to do is you're creating a contingency table of how frequently various values occur, right? And you're trying to see if they are independent of each other. Does smoking habit have anything to do with exercise, or vice versa? You know, again, not implying causation, but you're taking two categorical variables and seeing if these two variables are independent of each other. So the core idea between that is to convert this table to a set of percentages. So for instance, you would take each of these values and you would see how frequently they occur within each row, essentially, and similarly you would do that for each row. And finally what you would do is you would create theoretical values for this table in accordance to the assumption of independence. So for instance, if I believed that these were completely independent, I would take the row wise sums and the column wise sums, and I would for instance conclude that row 1 there would be a 48.7% chance of seeing a particular value occur in a particular spot. So I would essentially say, look, since this is I'm getting that 48 so the numbers I'm getting are, for instance, out here it's 48.7, okay, and the number for this category is 41.5, and for this would be, I believe, the remaining, which is about 9.7%. 48, 41, yeah. But the idea is the following, right? The idea is that you get percentages based off of the sum of each row. So you do 7 plus 9 plus 12 plus 87, and you divide that by the total sum of all values, and that's how you get the 48.7%. Okay, now given that there's a 48.7% chance that you will find yourself in row 1, I ask you the question that if you were a heavy smoker, right, and there are a total of 11 heavy smokers, the number of heavy smokers that frequently exercise that I should expect is 11 times 48.7%. So just note the math that we did here. We computed the probability of being in each row. The way we did that is we took the sum of each row. So the sum of the first row is 7 plus 9 plus 12 plus 87, and we divided that by the sum of all the numbers here, and by doing that we got a number 48.7%. Okay, so we told ourselves the probability that if I did not know anything, that I would find myself in the first row is 48.7%. Now assume that I am a heavy smoker. Then there are a total of 11 heavy smokers. If I were to randomly guess whether I was a frequent exerciser or not, then my probability is nothing. The number of heavy smokers that frequently exercise, the expected value of that is nothing but the 11, which I get from adding 7 and 3 and 1 and multiplying that by the 48.7. Okay, and a small correction from before. So you would, this I know for a fact is 48.7. This probability is also 41.5. You would just need to compute the remaining to get this value, and that's close to about 10%. Okay, so I don't believe it's exactly 9.7%. That's why I'm correcting myself. But that's the core idea. The core idea is you calculate percentages based on frequency of occurrence, and then you come up with what is an expected value for each cell. Okay, once you come up with an expected value for each cell, and you can do that row wise or column wise. I explained it to you row wise, so I took each row, calculated a percentage, and then I calculated an expected value. But essentially what you've computed is a set of expected values out here. Okay, now you compare each original value. So you compare that 7. Okay, so I compare this 7 to what I get when I multiply 48.7 by 100, 48.7% times 11. I believe that's approximately like close to 5 point something. So what I'm essentially doing is I'm doing that 7 which I see minus that expected value, which is the 5 point dot that I see, and I'm squaring that, and I'm doing that for each cell, right? So I'm doing that for each row and each column, and thereby doing that for each cell, and I'm dividing it by that expected value. So this 5 will also come in the denominator. Okay, and that summation should essentially give me a chi-square distribution with r minus 1 times c minus 1 degrees of freedom. Now note that the chi-square distribution has only one parameter associated with degrees of freedom. So if you just expand this, you will get this formula, which is nothing but just linear algebra, r times c minus r plus 1. So you've just calculated a test statistic using this formula, and that test statistic should be chi-square distributed with this degrees of freedom. And again, you can use that same core concept to calculate a p-value associated with it, and thereby either reject the hypothesis. And and just as a refresher, what's the hypothesis here? The hypothesis, the null hypothesis, is that there is no relationship between this variable and this variable. That is, these two variables are independent of each other. And the alternate hypothesis is the rejection of that, right? That there is some relationship that, depending on whether you're a heavy, regular, or occasional smoker, that impacts whether you're going to be a frequent exerciser or not. I mean, it's not a causal relationship, but knowing this helps me say something about this other variable. Or it can be the other way around. Knowing that you're a frequent exerciser, does that help me in any way predict or in any way make a statement about your smoking habit, right? Is there some relationship, or are these two variables independent of each other? The null hypothesis being that they're independent of each other, and a very low p-value in this chi-square test statistic will enable you to reject that null hypothesis, or you would fail to reject that hypothesis. Okay, so I hope this gives you an idea of the two tests that we've introduced in inferential statistics that have to do with multiple samples, that just don't have to do with two samples. That's the ANOVA, or the analysis of variance, and the chi-square test of independence. In our next lecture, we are going to start with regression. Thank you.